Hello. I'm back with the second part of 10.1 sequences and series, and today we're going to focus on the series portion of it. Alright, this symbol right here. This is a symbol that represents series. It is the uppercase Greek letter for sigma. It is the symbol that represents summation notation. It is used to find the sum of the terms of a finite sequence. Alright, so summation notation down here at the bottom has different parts. First you have the summation symbol, which is sigma. So you may see summation and sigma used hand in hand because they mean the exact same thing. Alright, so summation notation uses a sigma symbol. Okay, down here at the bottom tells you where to start. So last week we talked about, or the other day we talked about sequences, and we learned that sequences go are sequences in a series that go from one number to the next and to the next. Okay, and this takes that sequence of numbers that's given, okay, and it adds them together to come up with the sum. Okay, so in this particular sequence, I'm looking at a sub I. The sequence starts with number 1, so this is where it starts. And the top number represents your upper limit, or where it ends. So the summation of a sub I as I equals 1 to n is equal to a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus whatever comes in between, all the way out to where it ends, which is a sub n. And we'll get more into that when we're looking at some examples. Okay, for example number 1, we're going to be finding the sum of each one of these series that's listed here. Now these series, I should point out, are finite sequences because I'm looking at a specific set of data rather than looking at a whole as the sequence goes on and on and on. So remember back to when we were finding sequences, we were given, it may have asked a question like, find the first 4 terms of the sequence. And how do we do that? We had to plug in 1, 2, 3, and 4 into a given equation. Okay, series is doing the exact same thing, except it's taking those answers that you would get from plugging in the n number, and it's adding those sequence numbers together. So in this instance, this summation symbol is telling me to find terms, the first term to the 5th term. So I'm looking for term number 1, term number 2, term number 3, term number 4, and term number 5. And I want to add them together. Well, how do I get those terms in the sequence? Well, it's telling me to multiply 3 times the number of the term. So I'm going to take 3 and I'm going to multiply it times 1 plus take 3 again, multiply it times 2, and I have to go all the way to where it tells me my upper limit is, which is 5. 3 times 3 plus 3 times 4 plus 3 times 5. All right, and then we work it out. 3 times 1 is 3, plus 3 times 2 is 6, plus 3 times 3 is 9, plus 3 times 4 is 12, plus 3 times 5 is 15. And then we get the sum of adding all of those numbers. 3 plus 6 plus 9 plus 12 plus 15. So 3 plus 6 plus 9 plus 12 plus 15 is going to be 45. All right. Look at problem number 2. Problem number 2 gives us the, tells us to find term number 3 is my lower limit up to term number 6. And here's how I'm going to do it. You're going to take 1 plus k squared. I should tell you that k and I are the exact same thing, so it doesn't matter what letter is down here. They mean the exact same thing. What we're focusing on is the number that's on the bottom, which is your lower limit, and the number that's on the top, which is your upper limit. Okay, so now I want to take 1 plus 3 squared plus 1 plus 4 squared, because now I'm going 3, 4, 5, and 6, plus 1 plus 5 squared plus 1 plus 6 squared. So now you've gotten from your lower limit all the way up to your upper limit, 3, 4, 5, and 6. All right, so now you can work it out. 3 squared is 9, 9 plus 1 is 10. Plus 4 squared is 16, plus 1 is 17. Plus 5 squared is 25, plus 1 is 26. Plus 6 squared is 36, plus 1 is 37. And now I want to add 10 plus 17. Hold on. 10 plus 17 plus 26 plus 37. And that gives us 90. Okay, last example. It wants us to find, excuse me for the table shaking, starting at 0 all the way up to the 8th term. So my lower limit is 0. My upper limit is the 8th term. And I am using the expression 1 divided by I factorial in order to get there. So again, I'm going to plug in 0, 1, 2, 3, 4, 5, 6, 7, 8 in for I, and then we're going to add our answers together. So I have 1 divided by 0 factorial is plus, sorry about that, 1 over 1 factorial, hopefully I don't miss out on 1, plus 1 over 2 factorial, plus 1 over 3 factorial, plus 1 over 4 factorial, plus 1 over 5 factorial, plus 1 over 6 factorial, don't let me run out of room, plus 1 over 7 factorial, plus 1 over 8 factorial. All right, so I know that 0 factorial is 1. 1 divided by 1 is 1. Same thing goes for 1 factorial. 1 factorial is 1. 1 divided by 1 is 1. So 1 plus 1 plus 1 over 2 factorial is 1/2 plus 1 over 3 factorial is 1 over 6, because 3 factorial is 3 times 2 times 1, and 3 times 2 times 1 is 6. All right, so now I'm going to break out a calculator. If you need to use Desmos, I can show you how to do that. Okay, move this over to the side. Find my Desmos calculator I have open. Here we go. And I want to go to a blank graph. Okay, and then I'm going to make this side, if I can, bigger once I type something in there. So I want, just to show you you could do this in your calculator, 1 divided by 4 factorial, and I want to change it to a fraction by clicking on the blue circle, is 1 over 24 plus, okay, so 24 times 5, so I'm going to enter, is 120, so that's 1 over 120. 120 times 6, 720. 1 over 720 is 1 over 6 factorial, plus 1 over 7 factorial, which is 720. It can get pretty big, times 7 is 5040, so 1 over 5040. Hopefully I did not skip one. 0, 1, 2, 3, 4, 5, 6, 7, and then the last one is 8. So I'm going to take 5040 and multiply that times 8, and I got 1 over 320. All right, then I have to add all of those up together. So 1 plus 1 plus 1/2 plus 1/6 plus 1/24 plus 1/120 plus 1/720 plus 1/5040 plus 1/4320. And my answer, I don't know if I could change this to a decimal. We'll try and see what happens. There it is as a fraction. So you can write 109,601 over 4,320, or your answer could be as a decimal because it's so big, 2.7, approximately 2.72. Example number 2 asks us to rewrite the series in sigma notation. And for this part, we are still going to use the Desmos calculator. You should still have access to the link I sent you in the Google slideshow for this week, of the table, the one with the table already set up for you with the equations. So that's the one that we are going to, default to. So hold on just a second. Let me pull it up. Here it is. Okay, so the first series has 3 plus 5 plus 7 plus 9. And we are going to assume that 3 is our first term, 5 is our second term, 7 is our third term, 9 is our fourth term, because it didn't give us any other specific information. So we are going to plug in those numbers for our y value: 3, 5, 7, 9. Okay, it looks like it's a linear equation, so we are going to use the linear format. And M is 2, B is 1. Okay, so I'm going to write this right underneath it. We know that the sequence itself is y equals 2x plus 1. Okay, now I'm going to rewrite this problem using sigma notation. So the first thing I need is one of those E-looking things, the sigma symbol. Okay, and you can either use K or I. It does not matter for the bottom portion. Our bottom limit or lower limit is 1 because we started with the first term. Our upper limit is 4 because we have a maximum of 4 numbers in our sequence. Okay, the expression used to get there is 2, and I have to replace the x with k now, k plus 1. And now you have just written it in sigma notation. Okay, I'm going to do the same thing for B. B has numbers 2 plus 4 plus 2 plus 4. Okay, I'm not asking you to add those numbers together. No, that's not what I'm asking you to do. I'm asking you to find the series, okay, the notation for it, sigma notation. So that includes finding the equation for the sequence of numbers that's given. Okay, all right, so now I want to look at the R value because clearly it is not linear. Okay, and I'm going to keep scrolling. It is not quadratic because the R value is nowhere near 1. Uh-oh, here we go. Ding, ding, ding. The R value is 1 here. It is exponential. Okay, so our equation is y equals, I like to write this information down. And I get where I'm plugging in the numbers from the parameter section of this format. And it tells me to plug in 1 for A, -1 for B, and 3 for C. The y and the x stay exactly the same. So y equals 1, which you don't necessarily have to write, -1 to the x power plus 3. Okay, so now to rewrite that in sigma notation, I use the sigma symbol. All right, I'm going to use I this time. The lower limit is 1 because you're starting with the first term. I have 1, 2, 3, 4, a maximum of 4 numbers in this sequence. So 4 is your upper limit. And then the expression that you wrote down for your equation is the same expression that you're going to write over here, except in the place of ix, you're going to put I. So it's negative 1i to the I power plus 3. Okay? Last sequence. Go back up here to my table. And I'm going to put in 2 for the first term. 8 is the second term. 18 is the third term. And 32 is the fourth term. Quadratic, just by looking at the graph on the right hand side, it's got a U shape. So that's where I'm going. Quadratic. And look at there, the R squared value is 1. All right. And it says my parameters are A is 2. B is 0. And C is 0. As long as A is not a 0, then we are in good shape for quadratic. Okay, so I'm going to write this equation now. Y equals 2x squared. I don't have to write it if it's 0. Don't write the other terms because they're 0. 0 times anything is 0. So it'll be pointless to write that. All right, so now I'm going to rewrite it using sigma notation. Again, I'm going to use K. K is equal to 1 because it didn't tell me anything different. I'm assuming that this is the first term in the sequence. All right, if this is the first term, then that means 32 is my fourth term, and that's the upper limit. 4 is my upper limit. Not 32, it's 4 because you only have a total of 4 numbers in that sequence. I hope that makes sense. All right. And then the expression you are going to write is 2x squared, but instead of x, you're going to replace it with a k. So 2k squared. Summation of infinite series. So the last few examples we talked about finite series, and now we're looking at infinite series. The biggest difference between finite and infinite is your upper limit. The upper limit on infinite series you will see is infinity. That's why it's called infinite, because infinite continues on and on forever. It's where finite is a specific set of data. Okay, so we are going to, with knowing that information, we're going to take a look at finding the partial sum of infinite series. There is a way to find the summation of an infinite series, even when it goes on and on and on. It's just called finding the point of convergence, and that's a discussion for another day. All right, so let's look at example A here. And we are going to take the series, and it says to find the third partial sum. All that means is instead of going to infinity, we're actually going to change, our upper limit to 3, because the maximum it wants us to go is to the third, and it's called a partial sum because remember this series actually goes out to infinity, but we're only going out to the third term in the sequence. All right, so we do just like we did before. I'm going to rewrite this so you know that this is the summation of 3 over 10i. All right, so that's going to be 3 over 10 times 1 plus 3 over 10 times 2 plus 3 over 10 times 3. Okay, then that's going to give us 3 over 10 plus 3 over 100 plus 3 over 1,000. And I left the calculator up because we're going to use it. All right, so 3 divided by 10 plus 3 divided by 100 plus 3 divided by 1,000 is 0.3333, and it repeats. Okay, So that is the third partial sum, or you can change it to a decimal, not decimal or fraction, or it can be 333 over 1,000. But we all know that 0.333 is actually another way of saying 1/3, right? Okay. All right. So let's look at the second question. Looking at the infinite series to k, going from 1 to infinity, and it wants us to find the fifth partial sum. So again, this is changing the upper limit to 5. Okay, even though this is an infinite sequence, I only want the partial sum of when it converges at 5. Okay, so I'm going to rewrite. K is equal to 1. Upper limit is 5. 2k is the expression. So now I want 2 times 1 plus 2 times 2 all the way up to 5. 2 times 3 plus 2 times 4 plus 2 times 5. Alright, 2 times 1 is 2 plus 2 times 2 is 4 plus 2 times 3 is 6 plus 2 times 4 is 8 plus 2 times 5 is 10. And then I want to add 2 plus 4 plus 6 plus, and I'm adding it into the wrong spot here, 2 plus 4 plus 6 plus 8 plus 10. And I'm still adding it to the wrong spot. Sorry. There we go. 2 plus 4 plus 6 plus 8 plus 10. Third time's a charm is 30.